Imagine standing outside on a quiet night, looking up at the sky and seeing thousands of tiny lights scattered across the darkness, each one a star, maybe even a distant galaxy, and it feels like you're seeing everything there is. Like the entire universe is laid out in front of you. But what if that view, as vast as it feels, is only a small window, like looking through a keyhole into something far greater? The part of the universe we can actually see has a name, and it's called the observable universe, which simply means everything that light has had enough time to reach us from since the beginning of time. Because light, even though it moves incredibly fast, still takes time to travel. And that simple idea quietly shapes everything we know about space. So what does that really mean? It means that when you look at a star that's, say, 1,000 light years away, you are not seeing it as it is right now. You are seeing it as it was 1,000 years ago, like watching a delayed recording instead of a live moment. And the farther away something is, the further back in time you are seeing it. Almost like each point of light is a tiny time machine. Now here's where it becomes even more fascinating. The universe itself is about 13.8 billion years old, which sounds like an almost impossible amount of time to imagine, like trying to count every grain of sand on a beach, and then multiplying that over and over. But even with that enormous age, there is still a limit to how far we can see, because light from anything farther away simply hasn't had enough time to reach us yet. You might wonder, does that mean there's nothing beyond that limit? Is that the edge of everything? It's a very natural question, and many people imagine the observable universe like a giant sphere with us sitting at the center and a hard boundary at the edge, like the walls of a room. But that's actually not how it works at all. There is no wall, no barrier, no glowing edge where the universe suddenly stops. Instead, it's more like a horizon, similar to when you stand by the ocean and look out as far as your eyes can see. The water seems to end at some distant line, but it doesn't actually stop there. It just continues beyond what you can observe. In the same way, the observable universe is not the whole universe. It is simply the part we are able to see from our position, limited by time and light. And if you could somehow move to a completely different location, billions of light years away, your observable universe would look different, like opening a new window into a different part of the same vast reality. This idea can feel a bit strange at first, because it means that what we call the universe in everyday conversation is actually just a portion of something much larger, something that extends far beyond what we can ever directly observe. And yet everything we study, every galaxy we map, every distant explosion of light we detect, all comes from within this visible bubble around us. To give you a sense of scale, imagine drawing a circle around yourself, where every point inside represents something you can see, and everything outside represents what you cannot. And now imagine that circle being so large that even light, traveling at its maximum speed, would take billions of years just to cross it, like trying to drive across a country that is so wide you would never reach the other side, even if you never stopped, not for food, not for sleep, not ever. That is the size of the observable universe, and yet, as enormous as it is, it might still be just a small fraction of the whole. Sometimes people think that telescopes will eventually let us see everything. Like if we just build a powerful enough machine, we'll finally reach the edge and look beyond it. But that's another common misunderstanding, because this limit isn't about how strong our tools are. It's about the fundamental nature of time and light itself. No matter how advanced our technology becomes, we cannot see light that has not arrived yet. And there will always be regions so distant that their light will never reach us at all. So in a quiet way, the observable universe is not just a region of space, It is a boundary of knowledge, a limit to what we can directly experience and measure, and beyond it lies everything else, unseen, untouched, and perhaps forever unknowable. And as you sit with that idea, it raises a gentle question that lingers in the background. If what we can see already contains billions of galaxies, each with billions of stars, like countless grains of sand stretching across an endless beach, then what might exist beyond that horizon, in the vast darkness we can never look into? As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. As you continue to sit with the idea of the observable universe, it might start to feel a little strange that there are parts of reality we can never see, no matter how hard we try, and that naturally leads to a quiet question. Why can't we just see everything? Especially if the universe has been around for so long. The answer is surprisingly simple, and it all comes down to something we experience every single day, but rarely think about, which is the fact that light takes time to travel, and even though it moves incredibly fast, faster than anything else we know, it is still not instant, not immediate, not everywhere at once. Light travels at about 300,000 kilometers per second, which is so fast that it could circle the Earth about 7 times in just 1 second, like going around the entire planet over and over in the blink of an eye. And yet, when it comes to the vast distances of space, even that speed begins to feel slow, almost like walking across a giant desert that never seems to end. So what happens when something is extremely far away? Its light begins a journey toward us, moving as fast as it possibly can. But if the distance is too great, that light simply hasn't had enough time to arrive yet, and until it does, we have no way of seeing that object at all, not because it doesn't exist, but because its signal hasn't reached us. You can think of it like hearing thunder after seeing lightning during a storm, where the flash appears instantly but the sound arrives later. Except in space, there is no shortcut, no faster signal, and the delay can last not seconds, but millions or even billions of years. This creates a kind of natural limit, not a wall, but a delay barrier, where everything beyond a certain distance is still in the process of sending its light toward us, like messages traveling across an unimaginably large ocean, some of which may never arrive at all. You might wonder, if the universe is 13.8 billion years old, shouldn't we be able to see things up to 13.8 billion light years away and no farther? It sounds logical at first, but the situation is a bit more complex, because while light is traveling toward us, space itself is also stretching, gently pulling distant regions farther and farther away, almost like dots drawn on a balloon that is slowly being inflated, where the dots move apart, not because they are traveling across the surface, but because the surface itself is expanding. This means that some of the light we see today began its journey when those objects were much closer to us, but over time, the expansion of space carried them much farther away. So by the time their light finally reaches us, they are no longer where they used to be. They are now at distances far beyond what you might expect. But here's another question that naturally comes up. If light is always moving toward us, will we eventually see everything given enough time? It feels like that should be the case, like waiting long enough for every message to arrive. But the universe has a different plan, because the expansion of space is not slowing down, it is actually speeding up, driven by something we don't fully understand yet. And this creates a situation where some regions are being carried away from us so quickly that their light will never be able to catch up, no matter how long we wait. It's like trying to swim toward a distant shore, while the ocean itself is pulling you backward, faster than you can move forward, where no matter how hard you try, you will never reach the destination, not because of your effort, but because of the way the environment is changing around you. This is why there are parts of the universe that are permanently invisible to us, not hidden behind anything, not blocked or covered, but simply too far and moving away too quickly for their light to ever arrive. Many people imagine that the darkness beyond what we can see is empty, like a void where nothing exists, but that's not actually true. It's more like a region filled with things we simply cannot observe. Galaxies, stars, maybe even structures far larger than anything we've ever seen, all continuing on beyond our horizon, quietly existing, without ever sending us a signal we can receive. And in a way, this limitation shapes our entire understanding of the universe, because everything we study, every discovery we make, every map we draw of the cosmos is based only on the light that has reached us so far, like trying to understand an entire forest while only being able to see the trees within a small clearing. It doesn't mean our understanding is wrong, but it does mean it is incomplete, shaped by what is available to us rather than what fully exists. So as you think about the night sky again, with its calm and distant glow, it becomes something slightly different, not just a collection of visible stars, but a reminder that what you are seeing is only the part of the universe that has had enough time to introduce itself to you. While beyond that, stretching endlessly in all directions, are regions still on their way, still sending their light across the vastness, some of which will arrive far in the future, and some of which will never arrive at all, leaving behind a quiet and humbling realization that the universe is not only vast, but also patient, revealing itself slowly, one beam of light at a time. When we talk about why we can only see a certain part of the universe, everything quietly connects back to one simple idea: the age of the universe itself, because no matter how far your imagination stretches, there is still a starting point, a moment when everything began, and that moment sets a limit on how much of the universe has had time to reveal itself to us. Right now, scientists estimate that the universe is about 13.8 billion years old, which means that everything we see has been shaped by nearly 14 billion years of time, a number so large it can feel almost meaningless at first, like trying to picture counting one number every second without stopping. It would take more than 400 years just to reach 1 billion, and you would have to repeat that process nearly 14 times to match the age of the universe. So when you look up at the sky, you are not just looking into space, you are looking into a timeline that stretches back billions of years, where every distant object is showing you a different moment in that long history. But here's the important part: because the universe has a finite age, there is a limit to how far light could have possibly traveled since the beginning. And that limit defines the boundary of what we can see, like a clock that started ticking at the very beginning and has been counting ever since, with light moving outward in all directions, slowly filling space with information. You might wonder, what was happening at the very beginning, and could we see all the way back to that moment? It's a natural thought, almost like wanting to rewind a video all the way to the first frame. But the early universe was very different from what we see today. It wasn't filled with stars or galaxies. It was a hot, dense, glowing state where light couldn't travel freely, more like being inside a thick fog where you can't see more than a few steps ahead. It took time for the universe to cool down and become transparent, allowing light to finally move across space without constantly being scattered. And only after that moment could light begin its long journey toward us, carrying information about distant regions. So even though the universe is 13.8 billion years old, we are not seeing all the way back to the exact beginning, but rather to the earliest moment when light was able to travel freely, like the first clear image after a fog slowly lifts. This leads to a quiet but interesting question. If the universe has been around for 13.8 billion years, does that mean the observable universe has a radius of 13.8 billion light years? It sounds like it should be that simple, but as you'll soon see, the answer is a bit more surprising, because space itself has not remained still during that time. Still, the age gives us a kind of cosmic clock, a way to measure how long light has been traveling, and it tells us that there are limits built into the universe, not because of barriers or edges, but because of time itself. You can think of it like turning on a flashlight in a completely dark room that keeps growing larger, where the light spreads outward, but the room expands at the same time. So even though the light has been traveling for a long time, there are always parts of the room it hasn't reached yet. And just like that, the universe has been expanding while light has been moving, creating a dynamic situation where distance and time are always connected. Many people imagine the universe as something static, like a giant stage where everything simply exists in place. But in reality, it is more like a story that is still unfolding, with new regions becoming visible over time as their light finally arrives, while others drift beyond reach. So the age of the universe is not just a number, it is a key that explains why we see what we see, and why there are limits to our view, shaping the size of our observable bubble and defining the horizon that surrounds us. And as you sit with that idea, it becomes quietly fascinating to realize that every photon of light reaching your eyes tonight has been traveling for some portion of those 13.8 billion years, like tiny messengers that have crossed unimaginable distances, just to arrive at this moment, carrying with them a piece of the universe history. Some of that light began its journey before Earth even existed, before the sun formed, before anything we recognize today had taken shape, and yet here it is, arriving now, allowing you to see a small part of a much larger story. And beyond that, still traveling, still on its way, are countless other signals that have not yet reached us, messages from regions so distant that their light is still crossing the vastness, slowly approaching, second by second, year by year, over timescales far beyond a human lifetime. It makes you wonder, what will the night sky look like in a distant future? After billions more years have passed, after more light has had time to arrive, after more of the universe has had a chance to reveal itself, will the sky become more crowded, more filled with distant galaxies? Or will other forces change what we are able to see? These are questions that gently lead forward, but for now, the age of the universe remains one of the most important pieces of the puzzle, quietly setting the stage for everything we can observe, and everything that still remains hidden beyond the horizon. At first, it feels like everything should be simple. The universe is about 13.8 billion years old. Light travels 1 light year per year, so the farthest things we can see should be about 13.8 billion light years away, like measuring distance with a steady, predictable ruler. But when scientists looked more closely, they found something surprising, something that seems to break that simple logic, because the observable universe is not 13.8 billion light years across. It is actually about 93 billion light years wide, which means from one side to the other, it stretches far beyond what you might expect, almost like discovering that a road you thought was a few kilometers long actually wraps around the entire planet. So how can that be possible? How can we see things that are now much farther away than the time light has had to travel? The answer comes from something that is easy to overlook, which is that space itself is not staying still while light moves through it. Instead, space has been expanding the entire time, stretching like a soft, flexible fabric, and this changes the way distances work in the universe. To picture this, imagine drawing 2 dots on a balloon and then slowly inflating it as the balloon expands. The dots move farther apart, not because they are sliding across the surface, but because the surface itself is stretching. And if you imagine a tiny ant walking from one dot toward the other, the path it travels keeps getting longer as the balloon grows, even though the ant keeps moving forward the whole time. Light behaves in a similar way as it travels across the universe. It keeps moving toward us, always at the same speed, but the space it is crossing is stretching as it goes, which means the distance between where the light started and where it ends up becomes larger over time. This leads to a quiet but fascinating realization. When we say a galaxy is 46 billion light-years away, which is about half of the observable universe's width, we are not saying that its light traveled that full distance in a straight, unchanging space. Instead, we are describing how far away that galaxy is now, after billions of years of expansion have stretched the distance, almost like measuring how far apart 2 points have drifted after a long, slow separation. You might wonder, does this mean light somehow traveled faster than it's supposed to, breaking the rules of physics? It's a common thought, but the answer is no, because light is still obeying the same speed limit. It never moves faster than it should. What changes is the space around it, not the light itself, and that distinction is what allows these enormous distances to exist without breaking any fundamental laws. Another way to picture it is like standing on an airport walkway that is moving backward while you walk forward. You are still walking at your normal speed, but the distance between you and where you started can grow much larger depending on how the walkway moves. And in the universe, space itself acts like that moving walkway, quietly stretching everything apart over time. This is why the observable universe ends up being much larger than the simple age of the universe would suggest, because while light has been traveling for 13.8 billion years, the destinations it came from have been carried farther away during that time, like trying to reach a friend who keeps slowly stepping backward as you walk toward them. So by the time you finally meet, the total distance between where you started and where they are now is much greater than the path you originally crossed. And this expansion has been happening everywhere, in all directions, meaning that every distant galaxy we see today is much farther away now than it was when its light first began its journey, turning the observable universe into something far larger than a simple calculation would predict. Many people imagine space as empty and still, like a quiet room where objects just sit in place, but in reality, it is more like a living, stretching environment, constantly changing, gently pulling everything apart over immense stretches of time, so slowly that we cannot notice it in everyday life, but so powerfully that it shapes the entire structure of the cosmos. So when you hear that the observable universe is about 93 billion light-years across, it is not just a number, it is a story of movement, of light traveling across expanding space, of distances growing even as signals make their way toward us, and of a universe that is far more dynamic than it first appears. And as you sit with that idea, it naturally leads to another quiet question. If space can stretch like this, if distances can grow so dramatically over time, then what is happening right now, at this very moment, to the galaxies we see at the edge of our vision? Are they still drifting farther away, still being carried outward by the expansion of space, slowly moving beyond our reach? As you begin to picture the universe expanding and stretching in all directions, another quiet idea starts to take shape, something that sits at the center of everything we can observe, and that is the speed of light. Because no matter how vast space becomes, or how far galaxies drift away, there is one rule that remains constant, one limit that nothing can break, and that is that light has a maximum speed, a kind of universal speed limit that shapes how information moves through the cosmos. Light travels incredibly fast, about 300,000 kilometers every second, which is so quick that it could circle the Earth roughly 7 times in just a single second, like taking 7 full trips around the planet before you even have time to blink. And yet, even at that speed, the universe is so large that light still needs time, sometimes billions of years, to cross the distances between galaxies. This creates something very important, a natural boundary, not made of matter or energy, but made of time and motion. Because if something is too far away, its light simply cannot reach us yet, no matter how long we wait within our current moment. You might wonder, why can't anything go faster than light? Why is there such a strict limit in the first place? It's a question that has fascinated people for a long time, and while the deeper reasons involve the structure of space and time itself, the simple way to understand it is that light speed is built into the fabric of reality, like a rule that everything must follow. Similar to how no object with weight can suddenly disappear or pass through solid ground without breaking the laws we know. This limit applies not just to light, but to any kind of information, meaning that nothing can send a signal faster than this speed. No message, no movement, no influence, and because of that, everything we know about the universe is shaped by how long it takes for information to travel from one place to another. To make this feel more real, imagine trying to have a conversation with someone who is very far away, but every message you send takes years to arrive, and every reply takes just as long to come back. The farther apart you are, the longer the delay becomes, until eventually, the conversation becomes impossible. Not because either of you stop talking, but because the messages can no longer bridge the distance in any meaningful way. This is similar to what happens in the universe, where beyond a certain point, distances become so large that even light, moving as fast as it possibly can, cannot keep up with the expansion of space. And this creates a boundary around us, not a physical edge, but a limit to what we can ever observe. Many people imagine that if we had better technology, stronger telescopes, or more advanced tools, we could eventually see beyond this boundary, like upgrading from a small window to a larger one. But this is another common misunderstanding, because this limit is not about how clearly we can see. It is about whether the light has arrived at all. And if it hasn't, no amount of technology can reveal it, because there is simply nothing to detect yet. It's like trying to listen to a radio station that hasn't started broadcasting. No matter how good your receiver is, there is no signal to pick up. So the speed of light quietly defines the size of our observable universe, shaping the horizon beyond which we cannot see. And it also creates a kind of delay in everything we observe, where every image is slightly out of date. Every distant galaxy is a glimpse into the past, rather than the present, like watching a recording that is always playing with a delay. And this leads to another gentle question. If the speed of light limits what we can see, does it also limit what can affect us? Can something beyond our observable universe have any influence on us at all? The answer, in a simple sense, is no, because if no information can travel faster than light, then anything beyond that boundary cannot reach us, cannot interact with us, and cannot be observed by us in any direct way, making the observable universe not just a visual boundary, but also a boundary of interaction, a region where cause and effect can still connect. This makes our observable universe feel almost like a self-contained bubble, where everything inside can influence everything else, given enough time, but anything outside remains forever separate, like distant islands, drifting too far apart to ever exchange signals again. And yet, even with this limit, the universe still feels unimaginably vast, because within this observable region alone, there are hundreds of billions of galaxies, each containing billions of stars, stretching across distances so large that even light needs millions of years to travel between neighboring galaxies, like trying to cross an ocean so wide that you would spend your entire life moving from one shore to the next. So the speed of light, while it limits what we can see, also gives structure to the universe, creating a kind of order, a way for information to flow and for events to connect across space. And without it, the universe would be a completely different place, far less predictable and far harder to understand. And as you sit with this idea, it gently reshapes the way you think about distance and time, because in the universe, they are always linked together, always connected by the journey of light. And everything you see, every star, every galaxy, every faint glow in the night sky is part of a story that has traveled across space at the fastest speed possible, just to arrive here in this moment, within the quiet boundary defined by light itself. As you sit with the idea that light sets a limit to what we can see, another gentle realization begins to unfold, something that quietly changes how we picture the entire universe, and that is the fact that space itself is not still, not fixed, but constantly expanding, slowly stretching in every direction. Even right now, as you read these words, it might feel natural to imagine galaxies moving through space, like cars traveling along a road, drifting farther apart as they go. But that picture is not quite accurate, because in reality, it is the road itself that is stretching, carrying everything along with it, almost like drawing dots on a rubber sheet, and then gently pulling it outward, where each dot moves away from the others, not because it is actively traveling, but because the surface beneath it is growing. This idea can feel a little strange at first, because we don't experience it in everyday life. You don't see your room expanding, or the distance between buildings slowly increasing, and that's because this expansion is extremely subtle on small scales, held together by forces like gravity and atomic bonds. But across the vast distances between galaxies, where there is very little to hold things in place, this expansion becomes noticeable, and over billions of years, it becomes incredibly powerful. So what does this actually look like? Imagine placing tiny marks on a balloon and then inflating it slowly. As the balloon grows, every mark moves away from every other mark, and the farther apart two marks are, the faster they appear to separate, not because one is moving faster than the other, but because there is more space between them to stretch. This is exactly what we observe in the universe, where distant galaxies appear to be moving away from us. And the farther they are, the faster they seem to recede, creating a pattern that is the same in every direction, as if everything is expanding outward at once. You might wonder, does that mean we are at the center of the universe, with everything moving away from us? It's a very common thought, but the answer is no, because this expansion looks the same from any point in space, like standing on any dot on that balloon. Wherever you are, it will seem like everything else is moving away from you, not because you are special, but because the surface itself is expanding everywhere at once. This is one of those ideas that feels simple once you see it, but a bit confusing before that, because it challenges the way we usually think about motion and position. And this expansion has been happening since the very beginning. Ever since the universe started, space has been stretching, carrying galaxies farther apart over time, turning what may have once been a much denser, closer arrangement into the vast and open cosmos we see today. To give you a sense of scale, imagine two galaxies separated by a certain distance, and now imagine that distance slowly doubling over billions of years, like 2 points on a stretching fabric, being pulled farther and farther apart until the space between them becomes so large that even light takes millions or billions of years to cross it. This expansion is not something we can stop or reverse. It is a natural part of how the universe evolves, shaping everything from the distribution of galaxies to the limits of what we can observe. And it also connects back to something we talked about earlier, because as space expands, it affects the journey of light, stretching the wavelengths of that light and increasing the distances it must travel, which is one of the reasons the observable universe ends up being so large. But here's another question that naturally comes up. If space is expanding, is it expanding into something, like growing into an empty void outside of itself? It's a very intuitive idea, almost like imagining a balloon expanding into the air around it. But in the case of the universe, there is no outside space that it is expanding into, because space itself is all there is. So the expansion is not happening into something else. It is simply happening everywhere within the universe at once, like the distances between all points, increasing without needing an external background. This can be one of the hardest ideas to fully picture, because our everyday experiences always involve things expanding into something. But the universe doesn't need an outside. It contains all of space within itself. And as this expansion continues, it leads to a quiet but important consequence, which is that galaxies that are already far away will become even more distant over time, slowly drifting beyond our reach, carried by the stretching of space itself. So the universe is not just large, it is becoming larger, not just vast, but growing more vast with every passing moment, like an ever-expanding ocean, where the distances between islands increase as the water stretches outward. And as you think about this, it gently shifts your sense of scale, because the universe is not a fixed stage where everything is set in place. It is more like a living process, continuously unfolding, continuously changing, where distances are not permanent, but evolving, shaped by the expansion of space itself. And within this expanding universe, we find ourselves in a small region where light has had time to reach us, surrounded by a horizon that is slowly changing as space stretches and time moves forward, leaving behind a quiet and fascinating thought. If everything is moving apart, if space itself is carrying galaxies away, then what is happening at the very edges of what we can see, where expansion and light meet, and where the limits of our observation begin to take shape? As the idea of an expanding universe settles in, it leads to something that at first sounds almost impossible, something that seems to go against everything we just understood about the speed of light. And that is the fact that some galaxies are actually moving away from us faster than light itself, which might immediately raise a quiet question in your mind. How can anything move faster than light if that is supposed to be the ultimate speed limit of the universe? It feels like a contradiction, like saying a car is going faster than the fastest possible speed. But the key to understanding this is remembering that it is not the galaxies themselves racing through space at that speed. Instead, it is the space between us and those galaxies that is expanding, stretching in such a way that the distance grows faster than light can travel across it. To picture this, imagine standing on that same expanding balloon again, watching a distant dot as the surface stretches. If that dot is far enough away, the space between you and it can increase so quickly that even if a tiny ant were trying to walk toward you at its fastest possible speed, the distance would still grow faster than it could close, making it seem as if the dot is moving away faster than anything can chase it. In the universe, light is like that ant, always moving forward at its maximum speed, but in some cases, the expansion of space outpaces it, creating regions where galaxies are effectively receding from us faster than light. This doesn't break any laws of physics, because the rule about the speed of light applies to motion through space, not to the expansion of space itself. And that distinction is what makes this possible. Without any contradiction, many people imagine this as galaxies shooting away like rockets, but that's not what's happening. They are more like passengers being carried apart by a stretching fabric, not actively speeding through space, but being separated by the growth of space itself. This leads to an interesting and slightly surprising consequence. Light emitted from those extremely distant galaxies may never reach us at all, because as it travels toward us, the space it must cross continues to expand, sometimes faster than the light can make progress, like trying to walk up an escalator that is moving downward, faster than you can climb, where no matter how long you keep walking, you never reach the top. You might wonder, if those galaxies are moving away faster than light, does that mean they are completely invisible to us? The answer is a bit more subtle, because we can still see some of them, but only as they were in the past, when they were closer, and the expansion had not yet stretched the distance as much. So the light we observe today began its journey long ago, when conditions were different, and since then, those galaxies have been carried much farther away, often beyond the point where new light they emit will never reach us. This creates a kind of one-way window into the past, where we can see ancient snapshots of distant galaxies, but we cannot see what they are like now, because their present-day light is no longer able to bridge the expanding gap between us. It's a bit like watching a ship on the horizon that slowly disappears, not because it vanishes, but because it moves beyond the range where its signals can reach you, leaving behind only the memory of what it once looked like. And this idea connects deeply with the limits of the observable universe, because it shows that there are regions that are not just far away, but permanently unreachable, places where even light cannot keep up with the expansion, creating a boundary beyond which information cannot travel back to us. Many people assume that everything in the universe is, in some way, connected and eventually observable, but this reveals something different, that there are parts of the cosmos that have effectively slipped beyond our ability to ever see them, not hidden behind anything, not blocked by dust or darkness, but simply carried away too quickly by the expansion of space. To give you a sense of scale, imagine trying to send a message across a distance so vast that even moving at the fastest possible speed, the gap keeps growing faster than your message can cross it, like shouting across a valley that is widening faster than sound can travel, until eventually your voice can no longer reach the other side at all. This is what happens with light in those distant regions, turning parts of the universe into places that are forever out of reach, at least from our point of view. And yet, those galaxies still exist, still forming stars, still evolving in their own way, even though we can no longer receive their signals, which creates a quiet sense of separation, like distant islands, drifting away into a fog where communication becomes impossible. As you sit with this idea, it gently changes how you think about distance and connection in the universe, because it shows that not everything that exists is accessible, not everything can be observed, and some regions are effectively isolated from us by the expansion of space itself. And this naturally leads to another calm and curious thought. If there are galaxies already moving away faster than light, slipping beyond our reach, then what does that mean for the boundary of what we can see? And how does this define the horizon that surrounds our observable universe? As you begin to picture galaxies drifting away, faster than light, carried by the expansion of space itself, a new idea slowly comes into focus, something that feels almost like a boundary, but not in the way we usually imagine. And this idea is known as the cosmic horizon, which is the limit beyond which we can never receive any information, no matter how long we wait. It's not a wall, not a surface, not something you could travel to and touch, but more like a line drawn by time and motion, a quiet boundary that separates what we can eventually see from what will forever remain out of reach. To understand this, imagine standing in a vast open field at night with a small lantern, and the light from that lantern spreads outward in all directions, slowly illuminating the ground. But at the same time, the field itself is expanding, stretching outward faster and faster the farther you look, and beyond a certain distance, the ground is moving away so quickly that the light from your lantern will never reach it, no matter how long the lantern continues to shine. That distant region is still there, still part of the same field, but it will never be lit, never be seen. And in the universe, the cosmic horizon works in a similar way, marking the boundary between regions whose light can reach us and regions whose light never will. You might wonder, is this the same as the edge of the universe? Is this where everything ends? It's a very natural question, but the answer is no, because the cosmic horizon is not an edge in space. It is a limit in what we can observe, and beyond it, the universe likely continues, just as richly as it does within our view, filled with galaxies, stars, and structures we can only imagine. Many people picture the universe as having a clear boundary, like the walls of a room or the edge of a map. But in reality, it is more like standing in a dense fog where you can only see a certain distance in every direction, and beyond that, things continue, even though they are hidden from view. The cosmic horizon is like that fog limit, except instead of being caused by mist or darkness, it is created by the combined effects of light travel time and the expansion of space. And here's something that makes it even more interesting. This horizon is not fixed. It changes over time, slowly shifting as the universe evolves, because as time passes, light from more distant regions has more time to travel toward us, allowing new areas to come into view, almost like watching the fog slowly lift and reveal more of the landscape. But at the same time, the expansion of space is also accelerating, pushing some regions away faster than light can catch up, which means that while some areas are becoming visible, others are slipping beyond reach, creating a dynamic balance where the boundary of what we can observe is always in motion. You might ask, if the horizon is changing, does that mean we will eventually see everything if we wait long enough? It feels like a hopeful idea, like patiently waiting for the entire universe to reveal itself. But the reality is more complex, because while some light will reach us in the future, there are regions so distant and moving away so quickly that their light will never arrive at all, meaning there will always be parts of the universe that remain permanently hidden from us. It's like standing by the ocean and watching ships on the horizon. Some slowly come into view as they approach, while others drift away and disappear, never to be seen again, not because they stopped existing, but because they moved beyond the distance where their light can reach your eyes. This creates a quiet sense of limitation, not in a negative way, but in a way that gently reminds us that our view of the universe is shaped by fundamental boundaries, by the way time and space interact, and by the simple fact that information takes time to travel. To give you a sense of scale, imagine a boundary so vast that even light, traveling non-stop for billions of years, is only just reaching it, like trying to cross a distance so large that even moving at the fastest possible speed, it takes longer than the entire history of human civilization, multiplied thousands of times. And beyond that boundary, there are regions that are effectively disconnected from us, not in the sense that they are separate universes, but in the sense that no signal from them can ever reach us, making them forever outside our observable reality. Many people find this idea a bit unsettling at first, because it suggests that there are limits to what we can know, that no matter how advanced our technology becomes, there will always be parts of the universe we cannot directly observe. But at the same time, it also adds a sense of mystery, a reminder that there is always more beyond what we can see. And as you sit with this idea, it gently shifts your perspective, because the cosmic horizon is not just a boundary. It is a quiet marker of possibility, showing us that the universe extends far beyond our view, stretching into regions we can never explore with our eyes, but can still imagine with our curiosity. And this naturally leads to another calm question. If there is no true edge, if the cosmic horizon is only a limit to what we can observe, then what does the universe actually look like beyond that boundary? And does it continue endlessly? Or does it take on a shape that we cannot easily picture? As the idea of the cosmic horizon settles in, it naturally brings up a quiet and very human question. One that almost everyone wonders at some point. Where is the edge of the universe? And what would it look like if you could reach it? It's easy to imagine something like a boundary, maybe a glowing wall, or a sudden drop into darkness, like the edge of a cliff, where everything simply ends. But this picture, as intuitive as it feels, is not how the universe works at all. Because in reality, there is no physical edge, no border you could travel to, no place where space suddenly stops. Instead, what we call the edge is really just a limit in what we can observe, shaped by light, time, and expansion, rather than something built into space itself. To understand this, it helps to think about the surface of the Earth, which might feel flat when you're standing on it, but if you travel far enough in one direction, you don't reach an edge, you simply keep going and eventually return to where you started. Because the surface is curved, not bounded by a sharp end. In a similar way, the universe may not have an edge at all, but instead could extend in a way that doesn't require a boundary, either continuing infinitely or curving in a higher dimension that we cannot easily picture. You might wonder, if there's no edge, then what exactly are we seeing? When we look out into space and reach the limit of our view, the answer is that we are simply reaching the point where light has had enough time to arrive, like standing in a fog where your vision fades, not because there is a wall, but because you've reached the limit of what light can reveal to you. Beyond that, space continues, just as real, just as full of structure, but hidden from direct observation. Many people imagine the universe as something contained, like a box with boundaries. But this is another common misunderstanding, because the universe does not sit inside anything larger. It is not surrounded by an empty void, waiting beyond its edges. Instead, it includes all of space itself. So asking what lies outside the universe is a bit like asking what is north of the North Pole. It's a question that sounds meaningful, but doesn't quite apply in the way we expect. This can feel a little difficult to picture, because our everyday experience always involves edges and boundaries. Rooms have walls, oceans have shores, objects have surfaces, but the universe operates on a different level, where space can exist without a defined edge, stretching in ways that don't require a stopping point. And this brings us back to the idea of the observable universe, because what we often call the edge is really just the farthest distance from which light has reached us. So far, like a circle drawn around us that marks the limit of our current view, not the limit of existence itself. To give you a simple comparison, imagine sitting in the middle of a large, dark field with a flashlight. The light spreads outward, illuminating a circular area around you, and beyond that circle, everything remains dark. Not because the field ends there, but because your light hasn't reached any farther. And if your flashlight were stronger or had more time to shine, that circle would grow, revealing more of the field. In the universe, light from distant objects plays the role of that flashlight, and our observable region is the area that has been illuminated so far, while everything beyond remains unseen. You might ask, if there is no edge, could you travel forever in one direction without ever stopping? It's a fascinating thought, and depending on the true shape of the universe, which we are still trying to understand, the answer could be yes. You could keep moving without ever encountering a boundary, either continuing infinitely or eventually looping back in a way similar to traveling around the Earth, but on a much larger and more complex scale. Many people find this idea both calming and a little unsettling, because it removes a sense of a final boundary, replacing it with something more open, more continuous, where space does not end, but simply extends. And as you think about this, it gently shifts your understanding of what the universe is. Because instead of being a contained object with edges and borders, it becomes something more like a vast, seamless expanse, where limits exist not in space itself, but in what we are able to observe and interact with. So when we talk about the edge of the observable universe, we are really talking about a horizon, a boundary of visibility, not a physical structure, and beyond that horizon lies more of the same universe, continuing quietly in all directions. And this leads to a calm and lingering question that naturally follows. If there is no edge, if the universe does not stop where our vision ends, then what might exist just beyond that horizon? In the regions that are still hidden from us, waiting beyond the limits of light and time, as the idea of an edge that isn't really an edge begins to settle in, your attention naturally drifts just a little farther outward, toward that quiet boundary we've been talking about, the horizon of what we can see. And a simple question gently forms: what is actually out there, just beyond it? In the vast region where light has not yet reached us, it might feel tempting to imagine something completely different, something strange or empty or unfamiliar. But in truth, the most likely answer is also the simplest, which is that just beyond the horizon, the universe probably looks very much like the part we can already see. The same kinds of galaxies, the same kinds of stars, the same patterns of structure stretching across space, continuing outward like a repeating landscape that doesn't suddenly change when it passes out of view. To picture this, imagine standing on a long, open road that stretches far beyond what your eyes can see. The horizon cuts off your view, but you know the road doesn't end there. It continues, mile after mile, with more of the same scenery extending beyond your sight. In the same way, the observable universe is like that visible stretch of road, while everything beyond is simply more of the same cosmic landscape, continuing quietly in all directions. You might wonder, how can we be so confident about something we cannot directly observe? Isn't that just guessing? It's a fair question. And while we cannot see beyond the horizon, we can look at the patterns within our observable region and notice how consistent they are, how the universe appears similar no matter which direction we look. And from this, we infer that this consistency likely continues beyond our view as well. It's a bit like seeing the same type of trees spread across a large area and assuming the forest continues in the same way beyond the hill. You can't see over, not with absolute certainty, but with strong reason based on what you already observe. Many people imagine that beyond the horizon might be a completely different kind of space, maybe even empty or filled with something unknown, but current understanding suggests that there is no special boundary where things suddenly change, no transition zone where the rules shift. Instead, the universe appears smooth and uniform on very large scales, meaning that what lies beyond is probably just more galaxies, more clusters, more of the same structure we already know, extending far beyond our reach. And yet, even if it is similar, it still holds a quiet sense of mystery, because those regions are not just far away, they are also unobservable in a direct way, meaning we can never confirm their details with our own measurements. They remain just outside our window, always present, but never fully revealed. To give you a sense of scale, imagine looking at a coastline that stretches for thousands of kilometers, but you can only see a small portion of it at any given time, even though you know it continues far beyond your view with countless details, shapes, and features that you will never personally see, yet still exist as part of the same continuous landscape. In the universe, the horizon works in a similar way, marking the limit of what we can observe, while beyond it lies a continuation of the same vast structure. But here's another gentle question that often comes up. If the universe continues beyond the horizon, could there be other regions like ours, with their own galaxies, stars, and maybe even observers looking out at their own horizons? It's a fascinating thought, and many scientists believe that the answer is yes, that there are likely countless regions similar to our observable universe, each with its own view, its own slice of the larger whole, like countless overlapping circles drawn across an endless surface, each representing what can be seen from a different point. This idea quietly changes the way we think about our place in the universe, because it suggests that what we see is not unique or central, but just one small portion of a much larger reality, one window among many, each limited by the same rules of light and time. And even though we cannot directly observe beyond our horizon, the idea that the universe continues smoothly gives a sense of continuity, a feeling that what lies beyond is not something completely alien, but rather a natural extension of what we already know. Still, there is a subtle layer of uncertainty, because no matter how strong our reasoning is, there will always be a part of that region that remains unknown, not because it is hidden on purpose, but because it is simply too far for its light to reach us. And as you sit with this thought, it creates a calm sense of curiosity, not a need for immediate answers, but a quiet awareness that the universe extends beyond what we can see, filled with more of the same structures, more of the same patterns, and yet also holding details we may never fully uncover. And this naturally leads to another question, one that feels even larger and more open. If the universe continues beyond our horizon, stretching farther and farther in all directions, then does it ever truly end? Or could it go on forever without any boundary at all? As your thoughts move gently beyond the horizon, following that quiet question of whether the universe ever truly ends, another idea begins to form, one that feels both simple and almost impossible at the same time. And that is the possibility that the universe might be infinite, meaning it could go on forever without any edge, without any boundary, without ever stopping, no matter how far you travel. It's a concept that sounds easy to say, but when you try to truly picture it, it becomes something much harder to hold on to, because everything in our everyday experience has some kind of limit. A room has walls, a road eventually ends, even the ocean meets land somewhere, so the idea of something that never ends at all feels unfamiliar, almost like trying to imagine a number line that keeps going without ever reaching a final number. To get a sense of this, imagine walking forward in a straight line, taking step after step, hour after hour, day after day, and no matter how far you go, there is always more ground ahead of you. No wall to stop you, no edge to fall off, just a continuous path, stretching endlessly in front of you. And even if you walked for your entire life, and then for thousands of lifetimes after that, you would still never reach the end, because there is no end to reach. That is what an infinite universe would be like. Not just very large, but truly without limit. You might wonder, is the universe actually infinite? Or is it just extremely big? It's a question that scientists are still trying to answer, and the truth is, we don't yet know for sure, because we can only observe a limited region, and everything beyond that remains out of direct reach. So while our observation suggests that the universe is very uniform and consistent on large scales, which supports the idea that it could continue endlessly, we cannot confirm it with absolute certainty. Many people think that infinite simply means really, really big, but there is an important difference, because something very large still has an edge somewhere, even if it is unimaginably far away, while something infinite has no edge at all, no final boundary, no place where it stops. It's like the difference between a road that stretches across an entire continent and one that has no end in any direction, where no matter how far you travel, you never come closer to a boundary because there isn't one. And this leads to another quiet thought. If the universe is infinite, then everything we see, every galaxy, every star, every structure within our observable region, is just a tiny part of something that has no overall limit, like looking at a small patch of sand on a beach that stretches endlessly in all directions, where no matter how much you explore, you are always surrounded by more. This can feel both calming and a little overwhelming, because it removes the idea of a final edge, replacing it with something open and continuous, where space does not end, but simply keeps going. You might ask, if the universe is infinite, does that mean there are infinite galaxies, infinite stars, even infinite versions of similar regions like ours? It's a fascinating possibility, and while it depends on details we are still studying, an infinite universe would indeed suggest that there are countless regions beyond what we can see, potentially repeating patterns, not necessarily in identical ways, but in ways that follow the same physical rules, creating structures that resemble what we observe within our own horizon. To give you a simple comparison, imagine a patterned fabric that extends without end, where the same types of shapes and designs appear again and again, not in exactly the same arrangement, but following the same overall style. And no matter how far you move across the fabric, you keep seeing variations of the same pattern. In a similar way, an infinite universe would be filled with repeating structures, governed by the same laws of physics, creating a sense of continuity across an endless expanse. But here's another gentle question. If the universe is infinite, how did it begin? And how can something infinite have a starting point in time? It's one of those questions that doesn't have a simple answer, because the universe can be infinite in space, while still having a beginning in time, much like a line that extends infinitely. In both directions can still have a point where you choose to start counting. The concepts of space and time, while connected, do not always behave in the same way. And this highlights something important, which is that our intuition, shaped by everyday experiences, does not always match the deeper nature of the universe. And sometimes, the most accurate ideas are the ones that feel the hardest to picture at first. Many people find the idea of an infinite universe a bit unsettling because it removes the sense of a final boundary, but it also brings a quiet sense of openness, a feeling that there is always more, always beyond, always something extending further than we can imagine. And as you sit with this idea, letting it slowly settle, it gently reshapes the way you think about space, because instead of being something contained, something with edges and limits, it becomes something continuous and unending, stretching quietly in all directions. And this naturally leads to another calm and thoughtful question. If the universe is not infinite, if it does have a finite size, could it still exist without an edge, in a way that loops or curves back on itself, creating a space that is limited, yet has no boundary at all? As the idea of an infinite universe slowly settles in your mind, another possibility begins to take shape, one that feels just as strange, but in a different way. And that is the idea that the universe might actually be finite, meaning it has a limited size, and yet still have no edge at all, no boundary you could ever reach, no place where it suddenly stops. At first, this sounds almost impossible, because in everyday life, anything that is finite usually has an edge, a border, or a boundary, like a table with sides or a room with walls. So how can something be limited in size but still have no edge? The key to understanding this lies in the idea of curvature, the way space itself can bend or wrap around in ways that are not obvious from our normal perspective. A simple way to picture this is to think about the surface of the Earth, which is finite, meaning it has a limited area. But if you travel in any direction, you never fall off an edge. You simply keep moving and eventually return to where you started, because the surface curves back on itself. There is no edge on the surface itself, even though it does not go on forever. Now imagine something similar, but instead of a two-dimensional surface like the Earth, we are talking about three-dimensional space, where the entire universe could be curved in a higher dimension, wrapping around in a way that allows it to be finite, without having any boundaries. You might wonder, what would that feel like if you could travel through such a universe? It would mean that if you set off in a straight line and kept going for an incredibly long time, far longer than any journey we could currently imagine, you might eventually come back to your starting point, not because you turned around, but because space itself loops in a way that brings you back, like walking around the Earth, but on a much larger and more complex scale. To give you a sense of this, imagine walking along the surface of a perfectly round sphere. You never encounter an edge, you never reach a boundary, yet the total area you can walk across is limited, and if you keep going long enough, you will eventually return to where you began. In a similar way, a finite but unbounded universe would allow endless travel without ever reaching a stopping point, creating a space that feels infinite from within, even though it has a limited total size. Many people find this idea a bit difficult to picture because it requires thinking beyond the three dimensions we are used to, imagining space bending in ways that are not directly visible. But mathematically and physically, it is a valid possibility that fits with what we understand about the universe. You might ask, how can we tell if the universe is curved like this, or truly infinite? Scientists look for subtle clues in the way light travels across space, in the patterns of distant galaxies, and in the structure of the earliest light we can observe, searching for signs that space might curve back on itself. But so far, the universe appears very close to flat on large scales, meaning that if it is curved, the curvature is so gentle that it is extremely difficult to detect, like standing on a vast plain that looks completely flat, even though it might have a slight curve over enormous distances. This makes it challenging to determine whether the universe is truly infinite, or just so large and gently curved that it appears infinite within our observable region. Another question naturally comes up. If the universe is finite but unbounded, what is it expanding into? It's a question that feels almost unavoidable, because we are used to things expanding into something else, like a balloon expanding into the air around it. But in the case of the universe, there is no external space that it is expanding into, because space itself is what is expanding. So the growth happens within the universe, not into something outside of it. This can be one of the hardest ideas to fully grasp, because it goes against our everyday experiences. But it is an important part of how modern physics describes the cosmos. To make it a bit more intuitive, imagine again the surface of a balloon, but focus only on the surface itself, not the air around it. As the balloon inflates, the surface expands, and the distances between points on that surface increase. But from the perspective of someone living on the surface, there is no need to think about the outside, only the changing distances within. In the same way, the universe's expansion describes how distances between points in space increase without requiring an external space beyond it. And as you sit with this idea, it gently shifts the way you think about size and boundaries, because it shows that something can be limited without having an edge, can be complete without being enclosed, can exist in a way that doesn't match the simple shapes we are used to. Whether the universe is truly infinite or finite but unbounded remains one of the biggest questions we continue to explore, and both possibilities carry their own sense of wonder, one offering endless extension, the other offering a kind of cosmic loop that connects everything in a subtle and hidden way. And as this thought settles, another quiet question begins to form. If the universe has regions we can never reach, whether it is infinite or curved, then are there parts of space that are permanently beyond our view, places that we will never be able to observe, no matter how long we wait? As you begin to hold the idea of a universe that might stretch endlessly or curve back on itself, another quiet realization slowly comes into view, something that feels both simple and deeply humbling. And that is the fact that there are regions of the universe we will never see, not just far away for now, but permanently beyond our reach. No matter how long we wait, no matter how advanced our technology becomes, it's not because something is blocking our view, not because of dust or darkness or distance alone, but because of the way space expands and the way light travels, creating a limit that cannot be crossed. You might wonder, how can something exist and yet be forever invisible to us? How can there be parts of the universe that we can never observe, even in principle? The answer connects back to something we've been gently building up to, which is the combination of light's finite speed and the expansion of space working together to create regions where signals can never reach us. To picture this, imagine standing on a long moving walkway that is slowly carrying everything away from you. And now imagine someone far ahead trying to walk back toward you, step by step. But the walkway is moving faster than they can walk. So even though they are moving in your direction, the distance between you keeps growing. And no matter how long they try, they will never reach you. In the universe, light behaves in a similar way for extremely distant regions. It travels toward us at its maximum speed. But space itself expands so quickly that the gap continues to grow, preventing the light from ever arriving. This means that there are galaxies whose light will never reach Earth, not in 1 billion years, not in 1 trillion years, not ever, because the expansion has effectively placed them beyond a permanent horizon. Many people assume that given enough time, everything will eventually become visible, like waiting long enough for all distant signals to arrive. But this is one of those common misunderstandings, because the universe is not static, it is dynamic, and its expansion changes what is possible over time, creating a situation where some regions drift out of reach, faster than light can bridge the gap. To give you a sense of scale, imagine sending a message across a distance so vast that even moving at the fastest speed allowed by nature, the destination keeps moving away faster than your message can travel, like trying to catch a horizon that retreats faster than you can run, where the gap never closes, no matter how long you keep going. This is what happens with those unreachable regions, turning them into parts of the universe that are forever outside our observable reality. You might ask, do those regions still exist in the same way as the parts we can see? And the answer is yes. They are just as real, just as full of galaxies, stars, and cosmic structures, continuing their own evolution, forming new stars, merging galaxies, and unfolding their own history, even though we will never receive any information from them. It's a bit like distant lands separated by an ocean that is growing wider over time, where the people on each side continue living their lives, completely unaware of one another, not because they are hidden, but because the distance has become too great for any communication. This creates a quiet sense of separation in the universe, where not everything that exists is connected in a way we can observe, where some regions are effectively isolated by the very structure of space itself. And this idea also reshapes how we think about the future, because as the universe continues to expand, more and more regions will cross this invisible boundary, slipping beyond reach, meaning that the observable universe may actually become smaller in terms of what we can interact with, even as the total universe continues to grow. You might wonder, Does that mean the night sky will change over time? Will distant galaxies slowly disappear from view? The answer is yes, but on timescales so vast that they stretch far beyond human history. Over billions and trillions of years, distant galaxies will fade and vanish as their light can no longer reach us, leaving behind a quieter, emptier sky. This gives the universe a kind of evolving horizon, where what is visible changes over time, not because things stop existing, but because they move beyond the limits of what light can bring to us. Many people find this idea a bit unsettling at first, because it suggests that there are limits, not just to what we know now, but to what we can ever know. But it also carries a sense of quiet wonder, a reminder that the universe is larger than our ability to observe it, that there is always more beyond what we can see. And as you sit with this thought, it gently shifts your perspective, because it shows that our observable universe is not the full picture, but just a portion of a much larger reality, shaped by the paths that light can take, and the way space continues to stretch. And this naturally leads to another calm and curious question. If there are regions we will never see, shaped by the expansion of space, then what is driving that expansion? What is causing the universe to stretch in this way? And why is it happening faster over time? As the idea of unreachable regions settles quietly in your mind, it naturally leads to a deeper question, one that feels both simple and mysterious. At the same time, what is actually causing the universe to expand? And more importantly, why is that expansion speeding up instead of slowing down? For a long time, scientists expected that the expansion of the universe, which began at the very start, would gradually slow over time, like a ball thrown upward that eventually loses speed as gravity pulls it back, because all the matter in the universe, all the galaxies and stars, have gravity, and gravity pulls things together. It seemed natural to think that this pull would slowly resist the expansion, making it weaker as time passed. But when scientists carefully observed distant galaxies, measuring how fast they were moving away, they discovered something unexpected, something that changed our understanding completely, which is that the expansion is not slowing down at all. It is actually accelerating, meaning galaxies are being pushed apart faster and faster as time goes on, like a car that keeps gaining speed instead of gradually stopping. This discovery led to the idea of something we now call dark energy, a name that sounds mysterious, but really just describes an unknown form of energy that seems to fill all of space and drive this acceleration. You might wonder, what exactly is dark energy? Is it a substance, a force, or something else entirely? The honest answer is that we don't fully know yet, and that is part of what makes it so fascinating, because even though we can observe its effects, the way it causes the universe to expand faster, we still don't have a complete understanding of what it is made of, or why it behaves the way it does. To picture its effect, imagine placing dots on a stretchy sheet and then pulling the sheet outward. But instead of pulling it with your hands, imagine that the sheet itself is somehow generating its own outward push, gently stretching more and more over time. And as it stretches, the dots move farther apart, faster and faster. In the universe, dark energy acts like that, internal push, not pulling things together like gravity, but pushing space itself to expand. And what makes it even more interesting is that dark energy appears to be spread evenly throughout space, not concentrated in one area, but present everywhere, meaning that as the universe grows, there is more space, and therefore more dark energy, which in turn causes even more expansion, creating a kind of feedback effect where the expansion continues to accelerate. You might ask, how strong is this effect? Is it something we can feel or notice? On small scales like within our galaxy, or even between nearby galaxies, gravity is much stronger, holding stars, planets, and galaxies together, so we don't notice the expansion in everyday life. It doesn't pull apart atoms or stretch objects around us. But on the largest scales, across the vast distances between galaxy clusters, dark energy becomes dominant, shaping the overall structure and future of the universe. To give you a sense of scale, imagine two galaxies separated by millions of light years, a distance so large that even light takes millions of years to travel between them, and over billions of years to travel between them. Dark energy gradually increases that separation, stretching the space between them more and more, until the distance becomes so great that their light can no longer reach each other. This is why the expansion leads to those unreachable regions we talked about earlier. Because dark energy is constantly pushing space outward, increasing distances, and creating boundaries that cannot be crossed by light. Many people assume that gravity is the only major force shaping the universe. But this discovery shows that, on the largest scales, something else is at work, something that does the opposite of gravity, not pulling things together, but pushing them apart. And this raises another quiet question. If dark energy continues to drive expansion faster and faster, what will happen in the distant future? Will galaxies keep drifting apart until the universe becomes empty and dark? The answer appears to be yes, at least based on what we currently understand. Because as time goes on, more galaxies will move beyond our observable horizon, their light no longer able to reach us, leaving behind a smaller visible universe, even though the total universe continues to grow. It's a bit like watching lights in the distance slowly fade away, not because they turn off, but because they move too far for their glow to reach you. And this gives the universe a kind of long-term direction, where over extremely long timescales, it becomes more spread out, more isolated, with galaxies drifting farther apart and fewer connections between them. Many people find this idea a little unsettling because it suggests a future where the universe becomes quieter and more empty, but it also highlights how dynamic and evolving the universe is, shaped by forces we are still trying to understand. And as you sit with this idea, it gently deepens the mystery, because dark energy is not something we can see directly, not something we can hold or measure in a simple way, but something we infer from the behavior of the universe itself, like noticing the wind by watching how trees move. Even if you cannot see the air itself, it reminds us that even within the observable universe, there are still things we do not fully understand, forces that shape everything on the larger scales. And this naturally leads to another calm and thoughtful question. If dark energy continues to push galaxies apart, gradually isolating them, then what will happen to the connections between galaxies over time? And how will this change the structure of the universe as it continues to evolve? As the quiet influence of dark energy begins to take shape in your mind, gently pushing space to expand faster and faster, another consequence slowly comes into view, something that unfolds over unimaginably long stretches of time, and that is the gradual isolation of galaxies, a process where the vast cosmic web we see today slowly unravels, leaving galaxies more and more alone in the expanding universe. Right now, when we look out into space, we see galaxies grouped together in clusters and connected by long filaments, almost like a giant web stretching across the cosmos, where matter is not evenly spread, but gathered into structures that span millions of light years, like threads connecting distant points across a vast fabric. Our own galaxy, the Milky Way, is part of a small group of galaxies, including Andromeda and several smaller companions, all held together by gravity, moving in a shared region of space. But beyond these local groups, other galaxies are already drifting away, carried by the expansion of space, and over time this separation will continue to grow. You might wonder, will gravity eventually pull everything back together? Or will this expansion keep pulling things apart forever? The answer depends on the balance between gravity and dark energy, and based on what we observe, dark energy is winning on the largest scales, meaning that while gravity can hold nearby galaxies together, it cannot stop the overall expansion from separating distant ones. To picture this, imagine a cluster of small islands close together in the middle of an ocean, where the water between them is calm, allowing them to stay connected. But farther out, the ocean is stretching and pulling away, widening the gaps between distant islands until they drift beyond sight of one another. In the universe, local groups of galaxies remain bound, but everything beyond a certain distance continues to move farther away, slowly disappearing from view. Over billions of years, this process becomes more dramatic. As more and more galaxies cross the cosmic horizon, their light no longer able to reach us, fading from the night sky, not because they vanish, but because they move too far away for their signals to arrive. You might ask, what would the sky look like in such a distant future after this process has continued for a very long time? It would look very different from what we see today. Instead of a sky filled with countless galaxies, scattered across the darkness, there would be far fewer visible structures, perhaps only the galaxies within our local group remaining, while everything else has slipped beyond the horizon. It's a bit like standing in a city where lights once stretched out in all directions, but over time, those lights gradually fade and disappear until only a small cluster remains nearby, surrounded by darkness. This future isolation creates a kind of cosmic loneliness, not in an emotional sense, but in a structural one, where regions of the universe become more separated, more disconnected, each local group of galaxies evolving on its own, without interaction from the vast structures that once surrounded it. Many people imagine the universe as something that always looks roughly the same over time, but this shows that it is constantly changing, not just in small ways, but in its overall structure, becoming more spread out, more divided as expansion continues. And yet, within these isolated regions, gravity still holds strong. Galaxies within a group can merge, stars can continue to form, and local interactions can still shape the future, even as the larger universe fades from view. You might wonder, does this mean that future observers, billions or trillions of years from now, would have a completely different understanding of the universe? The answer is yes, because without access to distant galaxies, they might not even realize that the universe is expanding, or that there are vast structures beyond their local region. Their observable universe would be much smaller, much quieter, and they might believe that their small group of galaxies is all that exists. This creates a fascinating perspective where our current view of the universe, filled with distant galaxies and cosmic structures, is actually a temporary window, a moment in cosmic history where we can still see far across space before expansion carries those regions beyond our reach. To give you a sense of timescale, this process unfolds over billions to trillions of years, far longer than human civilization has existed, like watching a slow-motion change that takes place over a time span so vast that it is difficult to fully grasp, where entire galaxies drift away over periods longer than the age of the Earth multiplied, many times over. And yet, even though this future feels distant, the process is already happening. Galaxies are already moving away, already being carried outward by the expansion of space, slowly increasing the distances between them. As you sit with this idea, it gently reshapes how you think about connection in the universe, because it shows that while everything may have once been closer, more tightly linked, the future holds a gradual separation, a quiet unfolding, where galaxies become more isolated over time. And this naturally leads to another calm and curious question. If galaxies will eventually drift beyond our view, what is the farthest thing we can currently see? What is the oldest light that has reached us? And how far back into the history of the universe does that light take us? As the thought of galaxies slowly fading into the distance settles in, your attention gently shifts in the opposite direction, not farther outward into space, but deeper backward in time, toward the oldest light we can possibly see. And this leads to something truly remarkable, something that acts like a quiet glow surrounding us in every direction, known as the cosmic microwave background, or simply the CMB, which is the earliest light that has reached us from the universe's past. It might sound surprising at first, but when we look far enough into space, we are not just seeing distant galaxies, we are also seeing a faint, almost uniform glow that comes from a time long before stars and galaxies even existed. A time when the universe itself was young, dense, and filled with energy. You might wonder, what exactly is this light? And how can it still be here after so much time? The answer goes back to a period when the universe was much hotter and more compact, almost like a glowing fog, where light could not travel freely because it kept bouncing off particles in every direction, like trying to shine a flashlight through thick smoke, where the beam scatters and never travels very far. In those early moments, the universe was not transparent. It was more like an opaque glow, filled with energy but without clear paths for light to move across. Then, as the universe expanded and cooled over time, something important happened. It reached a point where particles combined to form simple atoms, and when that happened, light was finally able to travel freely, without constantly being scattered, almost like a fog lifting and suddenly allowing you to see clearly for the first time. That moment, when light was released to travel across space, created the cosmic microwave background, and that light has been traveling ever since, for about 13.8 billion years, slowly stretching and cooling as the universe expands, until today it appears as a very faint glow spread across the entire sky. To give you a sense of how faint it is, imagine a glow so subtle that it is like the warmth you feel from a distant candle across a large room, barely noticeable, yet still present everywhere. And in fact, this glow is not visible to our eyes directly, but we can detect it with special instruments that measure microwave radiation, revealing a detailed map of the early universe. You might ask, why is this light so important? What does it tell us? The answer is that it acts like a snapshot of the universe at a very early stage, giving us a picture of what things looked like when the universe was only about 380,000 years old, which is incredibly young compared to its current age, like seeing a photograph of a person as a newborn compared to how they look decades later. This makes the CMB one of the most powerful tools we have for understanding the early universe, because it shows us the starting conditions from which everything else evolved. And what's even more fascinating is that this glow is almost perfectly uniform, nearly the same temperature in every direction, with only tiny variations, small differences that are like gentle ripples on a calm surface. And these tiny variations are what eventually grew into the galaxies and large-scale structures we see today, meaning that everything we observe now, every star, every galaxy, every cluster, can be traced back to these small fluctuations in the early universe. Many people imagine that the universe began with fully formed structures, but the reality is much more gradual, starting from a nearly smooth state and slowly evolving over billions of years into the complex patterns we see today. You might wonder, if this is the oldest light we can see, does that mean we are looking as far back as possible? Is this the ultimate limit of our view into the past? The answer is yes, at least in terms of light, because before this moment, the universe was opaque, meaning no light from earlier times can reach us directly. It is like trying to see through a wall that blocks all visibility, no matter how strong your vision is. So the cosmic microwave background acts as a kind of boundary in time, marking the earliest moment we can observe using light, beyond which we cannot see directly, at least not with current methods. To give you a simple comparison, imagine trying to look through a dense fog that suddenly clears. You can only see as far back as the moment when the fog lifts, and everything before that remains hidden. Not because it doesn't exist, but because it cannot be seen. In the same way, the CMB marks the point where the universe became transparent, allowing light to travel freely. And as you sit with this idea, it becomes quietly profound, because it means that when you look out into space and detect this faint glow, you are seeing the oldest light that has ever reached us, a signal that has been traveling for billions of years, carrying with it a snapshot of the universe's earliest visible moment. It surrounds us in all directions, like a gentle echo from the beginning, a reminder of how everything started from a simple, nearly uniform state, and slowly grew into the vast and complex universe we see today. And this naturally leads to another calm and curious question. If the cosmic microwave background is the earliest light we can see, then what existed before that moment? What was the universe like when it was still opaque? And is there any way for us to understand that hidden part of its history? As the faint glow of the cosmic microwave background settles gently into your understanding, it naturally leads to a deeper and quieter question, one that feels like looking beyond a curtain that we cannot fully lift. What was happening before that light was released, before the universe became transparent, when everything was still hidden from view? It's a question that reaches back to a time even earlier than the oldest light we can see, a time when the universe was so dense and so hot that light could not travel freely, like being inside a thick, glowing fog where every beam of light is scattered in all directions, never able to move in a straight path. In that early state, the universe was filled with a kind of energetic soup, a mixture of particles and radiation packed closely together, moving rapidly, constantly interacting, and because of that, light could not escape. It kept bouncing, colliding, and scattering, never traveling far enough to carry clear information across space. You might wonder, if light couldn't travel freely, how do we know anything about this early period at all? It's a very natural question, because it seems like a hidden chapter, but even though we cannot see it directly with light, we can still learn about it through the effects it left behind, like footprints in the sand that tell you someone passed by, even if you didn't see them walking. The cosmic microwave background itself carries subtle patterns, tiny variations that reflect conditions from that earlier time, giving us clues about what the universe was like before it became transparent. And beyond that, scientists use other methods, such as studying the distribution of galaxies and the behavior of particles, to build a picture of how the universe evolved during those earliest moments. To help picture this, imagine trying to understand what happened in a room before the lights were turned on. You can't see what occurred directly, but you can look at the arrangement of objects once the lights come on, and from that, you can piece together what might have taken place in the darkness. In a similar way, we study the visible universe to learn about the invisible past. You might ask, how far back can we go? How close can we get to the very beginning? Our current understanding allows us to trace the universe back to a fraction of a second after its beginning, a moment so early that time itself feels almost abstract, like trying to measure something smaller than a blink. And during those first moments, the universe was incredibly hot and dense, with temperatures so extreme that particles could not form stable structures. Everything existed in a highly energetic state. To give you a sense of scale, imagine temperatures so high that even atoms, which are normally stable, could not exist, breaking apart instantly under the intense energy, like ice melting instantly when placed into a blazing fire, except on a much more extreme level. As the universe expanded, it cooled, gradually allowing particles to combine, forming protons, neutrons, and eventually atoms, leading to the moment when light could finally travel freely, creating the cosmic microwave background. But before that cooling happened, the universe was in a state that is very different from anything we experience today. More like a glowing, dense plasma, where everything was tightly packed together. Many people imagine the beginning of the universe as an explosion in space, like a burst that expands outward into an empty void. But that's a common misunderstanding, because the universe did not expand into space. It was space itself that expanded, meaning that the early universe was not a point exploding into emptiness, but a state where all of space was already present, just much smaller and denser than it is now. This can be a subtle but important shift in how we picture it, because it means that every region of space was part of this early state, not just a central location. You might wonder, what about the very first moment, the exact beginning? What happened at that point? This is where things become even more uncertain, because our current theories, while very powerful, cannot fully describe conditions at the exact starting point, often referred to as the Big Bang. And beyond a certain point, our understanding becomes less clear, like trying to see through a fog that grows denser the further back you look. Scientists are working to develop deeper theories that can describe those earliest moments more completely. But for now, there remains a boundary in our knowledge, not just in what we can observe, but in what we can fully explain. And yet, even with these limits, we have been able to piece together a remarkable story of how the universe evolved from a hot, dense beginning to the vast and structured cosmos we see today, all from the clues left behind in the light and matter around us. As you sit with this idea, it creates a quiet sense of wonder, because it shows that even though there are parts of the universe we cannot see directly, we can still reach toward understanding them using the patterns and signals that have traveled across time. And it gently reminds us that the universe is not only vast in space, but also deep in time, with layers of history that stretch far beyond what we can observe with light alone. And this naturally leads to another calm and thoughtful question. If our observable universe is just one region shaped by these early conditions, could there be other regions far beyond our horizon that formed in similar ways, perhaps even resembling our own part of the universe? As your thoughts drift back from the earliest moments of the universe and return to the vast space around us, a gentle idea begins to take shape, one that feels both simple and quietly profound. If our observable universe is just one region, one small window into a much larger whole, then could there be many other regions like ours, stretching far beyond what we can ever see? It's a natural question, almost like standing in a large forest and wondering if the trees continue beyond the hill in the same way they surround you now. Based on what we observe, the universe appears very uniform on large scales, meaning that no matter which direction we look, the overall structure looks similar, with galaxies spread out in comparable patterns, like a repeating texture across a vast surface. This uniformity suggests that our region is not special or unique, but rather one example of a common pattern that likely continues beyond our horizon. You might wonder, what would these other regions actually look like? Would they be identical to ours, or just similar in general ways? The answer is that they would likely follow the same physical laws, forming galaxies, stars, and structures in ways that resemble what we see, but not necessarily in exactly the same arrangement. Because even within our observable universe, no two regions are perfectly identical. Each has its own distribution of matter, its own history of formation, shaped by small variations that grew over time. To picture this, imagine a vast ocean filled with waves, where the general pattern of rising and falling water is the same everywhere. but the exact shape of each wave is different, creating a balance between sameness and variation. In the universe, these other regions would be like distant waves in that ocean, following the same rules, but forming their own unique structures. You might ask, how many of these regions could exist? Is there a limited number, or could there be countless ones? If the universe is infinite, then there could be an infinite number of such regions, each with its own observable horizon, each containing galaxies and stars, and perhaps even observers looking out into their own skies, seeing a universe that appears just as vast and complete as ours does to us. Even if the universe is finite but unbounded, there could still be many regions beyond our view, far more than we could ever count or explore. To give you a sense of scale, imagine a pattern repeated across a surface so large that even if you spent your entire life moving across it, you would only ever see a tiny fraction, like walking across a beach that stretches endlessly in all directions, where every step reveals more of the same kind of landscape, yet always with new details. In the same way, the observable universe may be just one small patch within a much larger cosmic expanse filled with similar regions. Many people find this idea both comforting and slightly surprising, because it suggests that the universe is not centered around us, not designed in a way that makes our location special, but instead follows the same rules everywhere, creating a sense of continuity across vast distances. And yet, even though these regions may be similar, they are also completely beyond our reach, separated by distances so great and by expansion so strong that no light from them will ever arrive, making them permanently unobservable to us. You might wonder, if we can never see these regions, how can we be confident they exist at all? The answer lies in the consistency of the universe. We can observe because the same physical laws appear to apply everywhere we look, from nearby stars to distant galaxies, and this uniformity suggests that there is no reason for those laws to suddenly change just beyond our horizon. It's like noticing that every part of a visible landscape follows the same patterns, and assuming that the hidden parts beyond the hill continue in the same way, not with absolute proof, but with strong reasoning based on what we can observe. Another gentle question arises: could there be regions so far away that they developed differently, perhaps with slightly different conditions or structures? It's possible that small variations in the early universe could lead to differences in how structures formed, creating regions with different arrangements of galaxies or different histories of formation. But as far as we know, the underlying laws remain the same, guiding the overall behavior of matter and energy across the entire cosmos. And this idea quietly reshapes how we think about the universe, because instead of being a single, isolated space, it becomes part of a much larger, repeating pattern, where countless regions exist beyond our view, each with its own story, each evolving over time, yet all connected by the same fundamental rules. As you sit with this thought, it creates a calm sense of scale, a feeling that what we see is not the whole, but just one piece of a much larger puzzle, one region among many, each hidden beyond its own horizon. And this naturally leads to another question, one that feels even more expansive. If there are many regions like ours, could there be something even beyond that? Not just more of the same universe, but entirely separate universes, existing independently, forming what some call a multiverse. As the thought of many regions like ours gently expands in your mind, it naturally opens the door to an even larger and more curious idea, one that stretches beyond the limits of a single universe, and that is the possibility of a multiverse, which suggests that what we call our universe might be just one of many, each existing in its own way, separate yet part of a much greater, whole. It's a concept that can feel almost like science fiction at first, but it arises from real attempts to understand the deeper nature of reality, especially when we follow certain theories about how the universe began and how space behaves on the largest scales. You might wonder, what exactly does many universes mean? Are these universes connected or completely separate from each other? The idea can take different forms, but one of the simplest ways to think about it is to imagine our universe as a single bubble within a vast unseen space, where other bubbles also exist, each one its own universe with its own regions, its own galaxies, and its own history, but separated in such a way that no light or signal can travel between them. To picture this, imagine a pot of boiling water where bubbles form and expand within the liquid. Each bubble is separate, with its own boundary, and while they may exist close to each other, they do not merge into a single continuous space. Instead, they remain distinct. In the multiverse idea, our universe would be like one of those bubbles, surrounded by others that we cannot directly observe. You might ask, why would scientists even consider such an idea? What leads to the possibility of multiple universes? It often comes from theories about the early universe, especially ideas about rapid expansion, sometimes called inflation, which suggests that space may have expanded in different regions, in slightly different ways, creating separate areas that grew into their own universes, each potentially isolated from the others. While we cannot observe these other universes directly, the mathematics behind these theories suggest that such a scenario could be possible. Many people imagine the multiverse as something chaotic or completely random, but it doesn't necessarily mean that, because each universe could still follow its own consistent rules, forming structures and evolving over time, even if those rules differ slightly from one universe to another. This leads to a fascinating question. Could the laws of physics be different in other universes, or are they always the same? Some versions of the multiverse idea suggest that different universes could have different physical constants, meaning things like the strength of gravity or the behavior of particles might vary, creating environments that are very different from our own, while other versions suggest that the laws remain the same, but the arrangement of matter and energy differs. To give you a simple comparison, imagine rolling a set of dice many times. Each roll follows the same rules, but the outcomes can vary, creating different patterns each time. In a similar way, different universes could share the same underlying principles, but develop in unique ways. You might wonder, if these other universes exist, could we ever detect them? Or are they forever beyond our reach? At the moment, there is no direct evidence that allows us to observe other universes, and it may be that they are completely inaccessible, separated by boundaries that no signal can cross, making them impossible to detect with current methods. This is one of the reasons the multiverse remains a hypothesis, an idea that is supported by certain theories, but not yet confirmed by observation. Many people think that if something cannot be observed, it should not be considered. But in science, ideas are often explored if they arise naturally from theories that successfully explain what we do observe. And the multiverse is one such idea, emerging from attempts to understand the early universe and the nature of space. And even though we cannot directly see other universes, the idea itself invites a broader way of thinking, where our universe is not the only stage for reality, but part of something much larger. To give you a sense of scale, imagine our observable universe as a single grain of sand, and now imagine countless grains spread across an endless beach, each one representing a different universe, each with its own internal structure, yet all part of a greater expanse that we cannot fully perceive. This comparison is not meant to be exact, but it helps capture the feeling of how vast the multiverse idea can be. You might ask, does this mean there could be another universe just like ours, with the same galaxies, the same stars, even similar conditions? Some versions of the multiverse suggest that with enough universes, patterns could repeat in ways that create similarities, though not necessarily exact copies. But this remains a speculative idea, something that invites curiosity rather than certainty. As you sit with this thought, it creates a quiet sense of openness, a feeling that reality may extend far beyond what we can see, not just in distance, but in the very number of universes that exist. And it gently reminds us that our understanding, while powerful, is still growing, still reaching outward, exploring possibilities that stretch beyond direct observation. And this naturally leads to another calm and curious question. If our universe could be one bubble among many, how might these individual universes form? And what would it mean for each one to exist as its own separate space within a much larger system? As the idea of a multiverse quietly expands in your mind, it naturally begins to take on a more detailed shape. And one of the most common ways to picture it is through the concept of bubble universes, where each universe exists like its own expanding bubble within a much larger background, separate yet part of a broader process that may be unfolding beyond our view. This idea often comes from thinking about how the early universe might have behaved during its rapid expansion, where different regions of space could have expanded at different times or in slightly different ways, forming isolated pockets that grew into their own complete universes. You might wonder what exactly is meant by a bubble in this context. Is it something with a surface or boundary, like a soap bubble? The comparison is helpful for visualization, but it's not exact, because unlike a soap bubble that has a thin film separating inside from outside, a bubble universe is not floating inside a familiar space. It is its own space, complete in itself, with its own dimensions, its own expansion, and its own internal structure. To picture this more clearly, imagine a vast invisible background, where small regions begin to expand, each one growing like a bubble, and within each of those regions space unfolds, galaxies form, stars ignite, and time flows, creating a complete universe inside each expanding region. From the inside, everything feels continuous and complete, just like our own universe does to us, with no obvious boundary or edge, even though from a broader perspective, it may be just one of many such regions. You might ask, how do these bubble universes form? What causes one region to become a separate universe? In some theories, this process is linked to the way space itself can expand unevenly, where certain areas undergo rapid expansion, sometimes called inflation, creating distinct regions that become isolated from one another as they grow, like pockets forming within a larger stretching fabric. Once separated, these regions continue evolving on their own, no longer able to interact with each other because the space between them expands too quickly for any signal to travel across. It's a bit like droplets forming in a mist, where each droplet becomes its own contained unit, even though they all originated from the same source. Many people imagine that if these bubbles exist, they might collide or interact. But in most models, the expansion is so strong that these universes quickly move apart, preventing any interaction, making each one effectively isolated from the others. You might wonder, if we are inside one of these bubbles, is there any way to detect the others? Any sign that they exist beyond our universe? At the moment, there is no clear evidence that allows us to observe other bubble universes directly, and they may be completely beyond our reach, not just far away, but separated in a way that prevents any information from crossing between them. This makes the idea difficult to test, placing it at the edge of what science can currently confirm. Still, it remains an intriguing possibility because it offers a way to explain certain features of our universe, such as why the laws of physics have the values they do, suggesting that different bubbles might have different conditions, and we happen to exist in one where the conditions allow structures like galaxies and stars to form. To give you a sense of scale, imagine a vast foam made of countless bubbles, stretching far beyond what you can see, and each bubble contains its own internal world, its own space and time, and from within any single bubble, the rest of the foam remains completely hidden. Not because it is far in the usual sense, but because it exists in a way that is not directly connected to the space inside the bubble. This comparison is not perfect, but it helps capture the idea that each universe can be self-contained, even if it is part of a larger structure. You might ask, does this mean that our universe has a boundary somewhere, like the surface of a bubble? From our perspective, the answer appears to be no, because within our universe, space seems continuous and without edge. And even if there is a broader structure beyond it, we do not experience it as a boundary we can approach or detect. This is one of the reasons why the idea of bubble universes can feel both fascinating and distant, because it suggests something beyond our observable reality, yet gives us no direct way to explore it. Many people find this idea both exciting and a little difficult to grasp, because it expands the concept of reality beyond a single universe, introducing the possibility that what we see is just one example among many. And as you sit with this thought, it gently shifts your sense of scale once again, because now the universe itself becomes just one part of a larger picture, one bubble. It creates a quiet sense of openness, a feeling that reality may be layered in ways we are only beginning to imagine, extending beyond not just distance, but beyond the very definition of what we call a universe. And this naturally leads to another calm and curious question. If these bubble universes exist, could the laws of physics inside them be different from ours, creating realities that behave in ways we might not even recognize? As the image of many bubble universes slowly settles into place, it opens up another quiet and fascinating thought, one that feels almost like stepping into a completely unfamiliar kind of reality. If there are other universes beyond our own, could the rules that shape them be different? Could the very laws of physics change from one universe to another? It's a question that gently challenges something we often take for granted, which is the idea that the laws of physics we observe are the same everywhere, always consistent, always reliable, like a set of rules that never change. No matter where you go, within our observable universe, this consistency appears to hold true. The same forces, the same behavior of light, the same patterns of matter, all following the same underlying principles, whether we look at nearby stars or distant galaxies. But when we begin to think beyond our universe, into regions we cannot observe, the possibility arises that these rules might not be exactly the same everywhere. You might wonder, what does it actually mean for physics to be different? How could the rules change? It could mean that certain fundamental values, like the strength of gravity or the way particles interact, might have slightly different settings, almost like adjusting the knobs on a machine that controls how the universe behaves. To picture this, imagine a recipe where small changes in the ingredients or their amounts can lead to very different results. One version might create something stable and structured, while another might produce something that cannot hold together at all. In the same way, small differences in physical constants could lead to universes that look very different from ours, perhaps with stars that burn differently, or with structures that form in unusual ways, or even with conditions where galaxies never form at all. You might ask, How likely is this idea, and why would the laws vary in the first place? Some theories suggest that during the early stages of cosmic expansion, different regions could settle into different states, like patches of a surface cooling in slightly different ways, each one ending up with its own set of conditions. In such a scenario, each bubble universe could carry its own version of physical laws, not completely random, but shaped by how that region evolved. Many people imagine that if the laws were even slightly different, everything would collapse or become chaotic, but that's not always the case. Some variations could still allow for stable structures, just in forms we might not immediately recognize. To give you a simple comparison, imagine building structures out of blocks. If the rules for how the blocks connect change slightly, you might still be able to build something stable, but it could look very different from what you're used to, with new shapes and patterns emerging. In the same way, different physical laws could lead to different kinds of cosmic structures, not necessarily chaotic, but unfamiliar. You might wonder, could there be universes where life as we know it could not exist at all? The answer is likely yes, because the conditions that allow stars, planets, and complex chemistry to form depend on a delicate balance of physical constants, and even small changes could prevent these processes from occurring, creating universes that are very simple or very different in structure. This idea leads to another quiet thought. Perhaps we observe the laws we do because they are the ones that allow observers like us to exist, a perspective sometimes called the anthropic principle, which suggests that the universe we see is one where conditions happen to support the emergence of observers. It's not that the universe was designed for us, but rather that we find ourselves in a universe where such conditions are possible. Many people find this idea intriguing because it connects our existence to the broader structure of reality, suggesting that among many possible universes, we are in one where the conditions align in a way that allows complexity and observation. But it's important to remember that this remains a way of thinking about the possibilities, not a final answer, because we still do not have direct evidence of other universes with different laws. You might ask, is there any way we could test this idea? Any way to know if physics changes beyond our universe? At the moment, it remains difficult, because if these other universes are truly separate, their properties may never be directly accessible to us, leaving us to explore the idea through theory and indirect reasoning. And yet, even without direct evidence, the possibility itself expands our understanding of what reality could be, showing that the laws we observe may be part of a larger range of possibilities. As you sit with this thought, it creates a quiet sense of openness, a feeling that the universe we know, with its familiar rules and patterns, might be just one version of many, one set of conditions among countless possibilities. And it gently reminds us that what feels fixed and unchanging within our experience may be part of a broader landscape of variation, stretching beyond what we can directly observe. And this naturally leads to another calm and curious question. If there are regions beyond our view, or even other universes, could there exist structures on such vast scales that they go far beyond anything we can currently imagine within our observable universe? As the possibility of different universes and different physical rules quietly settles in your mind, another thought begins to rise, one that feels both familiar and deeply expansive. If the universe continues far beyond what we can see, could there be structures out there that are even larger than anything we have ever observed, patterns and formations so vast that they stretch beyond our current sense of scale? Within our observable universe, we already see structures that are almost difficult to imagine. Galaxies grouped into clusters, clusters linked into superclusters, and these superclusters forming long filaments and walls that span hundreds of millions of light years. like an enormous web spread across space. If you tried to picture one of these structures, it would be like imagining something so large that even light, moving at its fastest speed, would take hundreds of millions of years just to cross it, like trying to travel across a distance so vast that entire civilizations could rise and fall many times before you reach the other side. And yet, even these enormous structures might not be the largest possible, because our observable universe is only a limited region, and beyond it, there could be even larger patterns extending across distances we cannot measure. You might wonder, what would something larger than these structures even look like? How can we imagine something beyond what we already struggle to picture? One way to think about it is to consider how patterns repeat at different scales, like looking at a coastline from different heights. Up close, you see small details, rocks and curves, but as you move higher, you begin to see larger shapes, bays and peninsulas, and from even higher, entire continents come into view, each level revealing a broader pattern. In the universe, we might be seeing only one level of structure, while beyond our horizon, there could be even larger patterns, like an even wider web, or arrangement that connects regions far beyond our observable limits. You might ask, is there any evidence that such larger structures exist, or is this purely speculation? Within our observable universe, we do see hints of very large formations, such as immense walls of galaxies and vast voids where very little matter exists, creating a kind of cosmic pattern that resembles a sponge or a network. And these structures already push the limits of what we expected to find. Some of these formations are so large that they span distances comparable to a significant fraction of the observable universe, like enormous bridges of galaxies stretching across space. But beyond that, we cannot directly observe what lies further out. So the idea of even larger structures remains an open question, guided by the patterns we already see, and the possibility that they continue or evolve on even greater scales. Many people imagine that the universe becomes completely random at large distances, but what we observe suggests a kind of order, a structure that emerges naturally from the way matter and energy interact over time, creating patterns that repeat and grow. This raises another quiet question. Is there a limit to how large structures can become, or could they continue growing without bound if the universe itself is large enough? The answer is not entirely clear, because the formation of structures depends on factors like gravity and expansion, which both shape how matter gathers and spreads out. And while there may be practical limits within certain regions, the overall size of possible structures could still be much larger than what we can currently observe. To give you a sense of scale, imagine stacking cities together to form countries, then countries into continents, and then continents into a single land mass, covering the entire planet. And then imagine extending that idea further, creating structures that span not just a planet, but distances so vast that even imagining them becomes difficult, like trying to picture something larger than all the oceans combined. In the same way, cosmic structures could extend beyond our current understanding, forming patterns that stretch across regions we cannot see. You might wonder, if such structures exist, would they change our understanding of the universe? Or would they simply be larger versions of what we already know? It could be a bit of both, because while they might follow the same basic principles, their scale alone could reveal new behaviors or patterns that we have not yet observed, much like how viewing something from a greater distance can reveal shapes that are not visible up close. And this idea gently reminds us that our current picture of the universe, as vast as it feels, is still limited, still based on what we can observe. And beyond that, there may be layers of structure that we have not yet uncovered. As you sit with this thought, it creates a quiet sense of openness, a feeling that the universe may hold patterns on scales far beyond what we can currently imagine, extending outward in ways that challenge our sense of size and distance. And it naturally leads to another calm and thoughtful question. If there are limits to what we can observe and understand, both in terms of distance and scale, then how much can we truly know about what lies beyond? And where do the boundaries of human knowledge begin to take shape? As the idea of structures larger than anything we can imagine gently settles in, it naturally brings with it a quieter and more reflective thought, one that is less about the universe itself and more about our place within it. How much can we truly know, and where do the limits of our understanding begin? It's a question that doesn't rush forward with clear answers, but instead invites a slower kind of curiosity, a recognition that even as our knowledge grows, there may always be boundaries shaped not just by distance, but by the nature of reality itself. When we look out into space, we rely on light to carry information to us. Every image, every signal, every faint glow we detect is something that has traveled across vast distances, like messages arriving from faraway places, and everything we understand about the universe comes from interpreting those messages. But as we've seen, there are regions where light will never reach us, places beyond the cosmic horizon, and because of that, there are parts of the universe that we cannot observe directly. No matter how advanced our tools become, you might wonder, does that mean we will never know anything about those regions, that they are completely beyond our understanding? The answer is not entirely simple, because while we may not be able to observe them directly, we can still make careful inferences based on the patterns and laws we observe within our own region, building models and ideas that extend beyond what we can see, like imagining the continuation of a landscape beyond a hill based on what lies in front of us. This is one of the strengths of science, the ability to reason beyond direct observation, to use evidence and logic to explore possibilities. But it also comes with limits, because there is a difference between what can be inferred and what can be confirmed. Many people think that science will eventually answer every question, that given enough time, we will uncover all the mysteries of the universe. But this is another common misunderstanding, because some questions may lie beyond the reach of observation entirely, not because we lack effort or intelligence, but because the structure of the universe itself prevents certain information from ever reaching us. To picture this, imagine trying to understand what is happening on the other side of a wall that no sound, no light, and no signal can pass through. You can make guesses based on what you know, but you can never directly observe or confirm what is there. In the universe, the cosmic horizon acts like that boundary, not a physical wall, but a limit on the flow of information. You might ask, does this mean there are truths about the universe that we can never fully know? It's a quiet possibility, one that many scientists acknowledge, because our knowledge is always tied to what we can observe and measure. And if certain regions or events are forever beyond observation, then they remain beyond complete certainty. But this does not mean that our understanding is incomplete in a negative way. Instead, it highlights the depth and richness of the universe, showing that there is always more beyond what we currently know, always new questions to explore, always new ideas to consider. To give you a sense of this, imagine reading a book where some pages are visible and others are permanently hidden. You can understand the story from the pages you have. You can even infer parts of what might be on the hidden pages. But there will always be sections that remain unknown, not because the story is incomplete, but because your access to it is limited. In the same way, our view of the universe is shaped by what is available to us, and beyond that, there may always be parts of the story that we can only imagine. You might wonder, is this limitation frustrating? Or Does it take away from the sense of discovery? For many, it does the opposite. It adds a sense of wonder, a reminder that the universe is not something we can fully contain within our understanding, that it extends beyond our reach in ways that invite curiosity rather than closure. It encourages a different kind of thinking, one that values exploration without expecting final answers, one that finds meaning in the process of learning rather than in reaching a complete end. And this idea also connects back to everything we've explored so far, from the limits of light to the expansion of space, from the cosmic horizon to the possibility of other regions and even other universes, all pointing toward a reality that is larger than what we can directly experience. As you sit with this thought, it creates a calm sense of perspective, a feeling that our knowledge, while powerful, is part of an ongoing journey, one that continues to unfold over time. It gently reminds us that the universe is not just something to be measured, but something to be explored, something that holds both answers and mysteries in balance. And in that balance, there is a quiet kind of beauty, a sense that even at the limits of our understanding, there is still something meaningful, something worth wondering about. And this naturally leads to another calm and reflective question. If our observable universe feels so vast and complete to us, yet is only a small part of a much larger reality, could it be that what we see gives us the illusion of completeness, even though there is so much more beyond our view? As the quiet limits of knowledge begin to settle in, there is another gentle realization that slowly follows, something subtle but deeply meaningful. And that is the idea that what we see of the universe can feel complete, even though it may only be a small fraction of what truly exists. When you look up at the night sky, especially in a place far from city lights, it can feel full, rich, and endless, filled with stars stretching in every direction, like a vast ocean of light. And it is natural to feel that you are seeing something whole, something complete. But this feeling, as powerful as it is, can also be a kind of illusion, not because what you are seeing is false, but because it represents only the part of the universe that has had enough time to reveal itself to you. You might wonder, why does it feel so complete if it is only a portion? The answer lies in how our perception works, because we tend to treat what we can see as the full picture, especially when it already feels vast beyond imagination. And the observable universe is indeed enormous, containing hundreds of billions of galaxies, each with billions of stars, like a field so large that even if you spent your entire life counting grains of sand, you would never come close to matching the number of stars within it. To give you a sense of scale, imagine standing on a beach that stretches for thousands of kilometers, with grains of sand covering every inch. And then imagine that each grain represents a star. Even then, the number of stars in the observable universe would still be greater, making it feel almost impossible to grasp. And because this visible portion is already so vast, it creates a natural sense that we are seeing everything, or at least most of it. But as we have explored, there are regions beyond our horizon, places where light has not reached us and may never reach us, meaning that what we see, as complete as it feels, is only a limited view shaped by time and distance. You might ask, does this mean our understanding is somehow misleading, or that what we know is incomplete in a significant way? It's important to understand that our knowledge within the observable universe is still accurate and meaningful. The patterns we see, the laws we observe, and the structures we study are real and consistent, but they are part of a larger whole that extends beyond our view. It's like reading a detailed chapter of a book and understanding it clearly, even though the book itself has many more chapters that you have not yet seen. The chapter is complete in itself, but it is not the entire story. Many people imagine that if we just build better telescopes, we will eventually see everything. removing this sense of limitation. But as we've seen, the boundaries of observation are not just about technology. They are built into the nature of light and the expansion of space, meaning there will always be a horizon, always a limit to what can be directly observed. This gives the universe a kind of layered reality, where what we see feels complete within its own context, but is actually part of something much larger. You might wonder, does this illusion of completeness affect how we think about our place in the universe? In a way, it does, because it can make us feel central or surrounded by everything that exists, when in reality, we are simply located within one region, one observable bubble, and beyond that, there are countless other regions that remain unseen. It's a bit like standing in a clearing within a vast forest, where everything you can see feels like the entire forest, even though beyond the trees, the forest continues far beyond your view. And this does not diminish the beauty or significance of what we see. Instead, it adds another layer of depth, a quiet reminder that there is always more beyond what is visible. To give you another simple comparison, imagine looking at the ocean from the shore. The horizon makes it seem like the ocean ends at a certain point, but you know that it continues far beyond, stretching across the entire planet. And even though your view is limited, it still feels vast and complete in the moment. In the same way, the observable universe gives us a view that feels whole, even though it is only part of a much larger reality. Many people find this idea both humbling and calming, because it shows that the universe is not confined to what we can see, that there is always more beyond, and that our perspective, while meaningful, is not the final one. It encourages a sense of curiosity, a willingness to explore and imagine what lies beyond the horizon, even if we cannot directly observe it. And as you sit with this thought, it gently shifts your understanding, because it shows that completeness is not always about seeing everything, but about recognizing the limits of what is visible and appreciating the part we can observe while remaining open to what lies beyond. It creates a quiet balance between knowledge and mystery, between what is known and what remains unseen. And this naturally leads to one final, calm realization. If the observable universe feels complete, yet is only a portion of a much larger whole, then perhaps what we see is not the universe itself, but simply the part of it that we are allowed to see. As all of these ideas slowly come together, from the limits of light to the expansion of space, from distant galaxies drifting away to the quiet horizon that surrounds us, there is one final realization that gently settles into place, not as a sudden conclusion, but as a calm understanding that feels almost obvious once you see it clearly. The observable universe is not the whole universe. It is simply the part we are able to see, and in a quiet way, this realization changes everything, not because it adds something new, but because it reframes everything we have already explored, showing that all the galaxies, all the stars, all the vast structures we have been imagining exist within a kind of visible bubble, a region defined by time, light, and motion, rather than by any physical boundary. You might wonder, why does this matter? Why is it important to recognize that what we see is only a part? The answer is not about limiting our understanding, but about expanding it. Because once you accept that there is more beyond what we can observe, the universe becomes something even larger, even more open, even more filled with possibility than it first appeared. It's like realizing that a map you have been studying, as detailed and complete as it seems, represents only one region of a much larger world, and beyond its edges, there are landscapes you have not yet seen, places that exist even if they are not drawn. This does not make the map less useful or less accurate. It simply places it within a broader context. In the same way, the observable universe contains everything we can measure and study, everything that has had time to reveal itself through light. But beyond that, there is more. perhaps far more, continuing in ways we can only imagine. You might ask, does this mean we will never fully understand the entire universe? It's possible, because our knowledge is tied to what we can observe. And if there are regions that can never send us information, then there will always be aspects of reality that remain beyond direct confirmation. But this does not take away from what we do know. Instead, it highlights the depth of the universe, showing that even within the limits of our observable region, there is already more than enough to explore, more than enough to inspire curiosity and wonder. Imagine holding a single drop of water from the ocean. Within that drop, there is complexity, movement, structure, enough detail to study for a lifetime. And yet, it is only a tiny part of a much larger ocean that stretches far beyond what you can hold. In the same way, the observable universe, vast as it is, may be just a small portion of a much greater whole. And this leads to a quiet shift in perspective, because instead of thinking of the universe as something contained, something with clear boundaries and limits, it becomes something open, something that extends beyond what we can fully grasp, where our view is just one window among many possible views. Many people find this idea both humbling and comforting, because it reminds us that we are part of something much larger, something that does not end at the edges of our observation, but continues quietly beyond. It also changes how we think about our place in the universe, not as the center, not as the focus, but as participants within one region of a much broader reality, observing what we can, learning what we can, while knowing that there is always more beyond. You might wonder, does this make the universe feel more distant or less connected? In some ways, it creates distance, because it shows that there are regions we can never reach or observe. But in another way, it creates a deeper connection, because it reminds us that everything we see, every star, every galaxy, is part of a larger whole, connected by the same underlying principles. Even if we cannot observe all of it directly, it's like being part of a vast landscape, where you can only see a portion, but knowing that the same ground continues beneath your feet and beyond your view. And as you sit with this final realization, there is a sense of calm that comes with it, a feeling that the universe is not something we need to fully contain or completely understand, but something we can explore, appreciate, and wonder about within the limits that naturally exist. The observable universe becomes not a boundary that confines us, but a window that allows us to glimpse a part of something much larger, something that extends beyond our sight in all directions. And within that window, there is already so much: countless galaxies, endless stars, vast distances that stretch far beyond everyday experience, enough to fill the mind with quiet curiosity. And beyond that window, there is more, not something separate, but a continuation, a larger expanse that remains unseen, yet still part of the same reality. So in the end, the observable universe is not the full story. It is the part of the story that has reached us, the part that light has carried across time, the part we are able to witness. And while it may feel complete, it is only a beginning, a glimpse into something far greater, something that continues quietly beyond the horizon, waiting not to be fully seen, but simply to be understood as existing, stretching outward in a way that gently reminds us that the universe is always larger than what we can see, and always will be.